Sta registrando. Okay, hello everyone. I'm pleased to announce Edoardo Voglino from SISSA. We'll talk about microstructures and phase boundaries in long-range lattice systems.
Okay.
Okay.
Okay, so our problem belongs to the macro environment of the problem of the system defined as a minimum principle of interaction energies from discrete system. So we will have the sum over 2 points on a discrete setting of some interaction energy depending only on the distance of the 2 points and the difference of a quantity assigned to that points. Okay, this problem in general is, it's quite general, so we will study actually simplification. We will only consider 2 non-zero kind of interactions, the one depending the one on distance 1, so the interaction between nearest neighbors, or the interaction between neighbors at distance m. Okay. And we also set the problem in a one-dimensional environment, so we will have some equispace points on a line. Okay, on a continuous setting, we are trying to pose an analogy with a continuous problem given by the Modica-Mortula type of functionals, in which we have these 2 terms. One, the one with psi 1 represent a double well potential, while psi m is a strictly convex perturbation. One can think of a parabola. And this problem has been studied a lot. I can even cite a paper by some our fellow PhD students at SISSA, Giuseppe and Davide, in collaboration with Margherita Solci. And what happens in this problem? So if we try to analyze when epsilon become really small, what are the minimizer? They will tend to be something of this form. So we will have a transition in the slope of the minimizing function from one value to another, that is one well of the double well potential, the double well function psi 1 to the other well. Okay, in the discrete setting, is happening something.
Can you go back to the slide? So you prime is the derivative and you m
is the derivative of order run.
Okay.
Okay. So in a discrete setting, T energy will be affected not only on the slopes, on the approximation of the slopes, but there will appear some microscopic oscillations. So our discrete function approximating this kind of behavior will be oscillating. And what actually is affecting the discrete energy is not the change in the slope, but more the change in the microscopic oscillation. So we will have 2 kinds of transition. One is called the phase transition, which is something like this, in which the slope we are approximating is changing. But there is also another kind of transition in which we have only one slope, and at some point the oscillation is changing. And in particular, one can think of it like change of the phase in the periodic pattern. So something like this. At some point, we repeat the oscillation, but with a different period. Okay, to study how this oscillation affects our energy, we will use the tool of gamma convergence, but we will see this is not enough. We will have to also apply some gamma convergence expansion. Okay, so some preliminary, we just present quickly how we can prove a gamma convergence result. So, okay, apart from the definition through gamma lin sup and gamma lin inf, what I really want to highlight is that the gamma limit will be a functional always lower semi-continuous. What I want to stress more is how we prove a gamma convergence result. So we need these two conditions. One is that for each sequence converging to some point, we want the limit functional evaluated in the limit point to be lower or equal than the limit of the approximating functional evaluated on the approximating sequence. And also we need a second condition, so that for each point there exists a sequence. We will call it the recovery sequence, such that the limit functional evaluated on the point is greater or equal than the lim sup of the approximating functional on the recovery sequence. The gamma convergence is a kind of functional convergence study to preserve the minimum of some energy, and also to have a kind of approximation of the minimizers. But to have these two results, we need a further condition, that is a equicursiveness condition, which is basically a compactness result on the level set of the sequence of functionals. Okay, so let's dive into the problem. We are considering a one-dimensional discrete domain. So actually we take an interval, let's say 0, 1. We define n+1 equispaced point on it. And we should actually work with functions that take some real values on each that point. However, it will be useful to define a functional setting that is going to comprehend each of those discrete domains. So to achieve this kind of embedding, it's useful actually to define some kind of different functional space. We will consider piecewise affine functions with the identification that our function will be identified with the piecewise affine interpolation on the sides. So actually, we need to define. We will actually divide our domain into n subinterval, and on each subinterval, the function will be affine. And we will also pose some periodic condition. It's not really periodicity, but the function minus a line LT is periodic. Okay, this is how we pose our boundary condition. Okay, the energy we will work with is something like the one I presented in the first slide, but I need some proper rescaling by epsilon n to have the correct study for the gamma limit. And also as I was saying, the domain will be the one I defined previously, but we are posing the problem in the greater environment of L1 log function. The condition on psi1, psi2, and psi-m are very weak. Actually, the continuity is not strictly required. You can find generalization for which you actually can work with Borel functions, at least at this level. Then we will make some further assumptions on the function psi1 and psi-m. What is really important is the last condition, that thanks to the Danforth-Pettis property is providing coerciveness for our problem. So the equicoerciveness kind of property we need for the gamma convergence. Okay, so there is a very well-known results. There are many generalizations in many articles. I cited one here, for which we know that that functional is gamma converging in the L1 topology to this kind of integral function, such that we have the integral from 0 to 1 of the convex envelope of some function psi we are going to define soon. And we are evaluating it on the derivative of the input function. And indeed, the domain of this energy is W11 with the periodicity condition the same as before. Okay, how is this function psi defined? It's done through this minimum problem. So we have psi-n plus the minimum of the average of psi-m, of psi-1 evaluated of some points, the average of which is exactly z, so the value we want. Notice that in the case psi-1 is convex, actually psi becomes the sum of psi-m and psi-1, so something really simple to work with. And for this reason, we are going to assume some non-convexity later on. We will denote as bold M Z the set of minimizer for this problem. Okay, I'm not going to show the proof of this gamma convergence result, but I want to still make some observations. At first, we will need to know what are the minimizer of the limit energy, and simply by the Jensen inequality, we can immediately see that the minimum is psi star star of L. The minimizer will be lines of the kind UT equals LT. But once we ask what this kind of minimum minimizers are approximated in the discrete setting, we will have two kinds of behaviors. When psi of L is equal to psi star star of L, so in areas in which psi is convex, we will have something like this. So the line will be approximated by some optimal oscillations. So oscillation in the sets MC, ML I defined previous slide. The critical case is when psi of L is strictly greater than its convex envelope. In this case, it will happen something like this. So we will have some piecewise affine function, and on each affine portion, we will have an approximation to optimal oscillations. However, we are not approximating the correct slope L, but some other slopes. So the behavior will be a little bit different. And it's actually this case which is carrying mostly energy in the transition. Okay, so let's see how we can build a recovery sequence for the minimizer, so the function ut equal LT. As I was saying, in the simple case, we just take the optimal oscillations, nothing really special. We only need to enforce the boundary condition, but this is not a problem. What's really interesting is the other case. So as I was saying, to recover psi-star-star we need to work with convex combination of the function psi. So we will need to find some other two slopes, L1 and L2, such that their convex combination is almost the convex envelope. And the convex combination of L1 and L2 is exactly L. In this way, we will build the recovery sequence through this kind of two oscillation with difference frequency. The bigger oscillation are the one of the slopes L1 and L2, so the piecewise affine function. And then the microscopic oscillation will be given by the optimal oscillations for the slopes L1 and L2. Okay. In this way, if we look at what is going on to the energy, to the discrete energy, we will have, apart from some small error, we will recover the convex combination that is going to give the psi-star-star of L. But now we have another error, I highlighted in blue, which is coming from the transition from one oscillation to the other one. And this kind of error is actually proportional to epsilon m. So if we want to highlight the energy we are carrying through the transition from one oscillation to the other, we need in some way to rescale this energy by epsilon m. Okay, and this is what I was saying. The parts concerning the transition is vanishing at the limit, so we need some further analysis through the study of first order expansion and gamma convergence. What does it mean? Is that we are going to study the gamma limit of another functional defined as the previous discrete functional minus the minimum of the limit energy, everything scaled by epsilon m. And as we were saying before, the minimum of the limit energy is nothing less than psi-star-star of L. So, for our results, and also for the case we were interested in, we are going to make some further hypotheses on psi1 and psi-m. They will be of two kinds. One, the structure. So we take psi1 to be a double well potential, so something that before a given threshold, say Z0, is behaving as a function W2, and after Z0 is behaving as a function W1, and those functions are convex. The convexity is a requirement to achieve a better structure for psi of L and psi-star-star. And as well, we will assume psi-m to be strictly convex. The other kind of hypothesis is the regularity hypothesis. So we will assume W1 and W2 and also psi-m to have C1 regularity. This is an hypothesis that maybe can be weakened, but it's required for some technicality in the proof. And okay, we are also taking psi1 continuous at least, and we still keep track of the coerciveness condition. So, what is the convexity affecting our function psi? Now we can write, again, using the double well potential structure and the convexity, we can write psi as the sum of psi-m plus a minimum between n plus 1 functions. So actually, in the discrete setting with the double well potential kind of structure, we have a behavior not as not only as a double well, but as an n plus one well kind of function. Instead, for psi star star, we have a result that is telling us that actually we have only two kinds of behaviors for the convex envelope. We either are in a good interval for which psi star star is equal to psi, or we are in some other kind of interval, which are disjoints, such that psi star star is equal to a straight line. So we are on a segment. Okay. So now we can describe a little bit better what will be this kind of approximating sequence of function, which we need because the only function such that our energy will remain finite at the limit are those approximating a minimum for the limit energy. So we either have the approximation of the straight line with optimal oscillation when we are in the good interval. In the other intervals, we will have something of this kind, but now I know that the slopes we are using are the two extremes of the interval we are in. Okay. So now our optimal set will be either the previous optimal set when L is in a good interval. Otherwise, it will be the union of the two optimal sets for the extreme point, the edge point of that interval. The domain of our limit function now is a little bit different from what someone can expect, because we will work on vectorial functions. And why vectorial function is because we want to catch the local, this function is representing locally the oscillation we are taking in the approximation. And as the oscillations are n periodic, we need n values to define those oscillations. And indeed, the derivative will exactly represent the slopes of the oscillations. And we will see that then those oscillations must belong to some optimal sets. And the function will be piecewise constant, except for a finite amount of jumps. And there will also be some periodicity condition as before. So now we need to find a convergence from scalar functions to vectorial functions, and we need to do it in such a way we are capturing the local oscillation. So we actually define these kind of interpolations, which are basically we take n consecutive small interval, and we look at the first small interval of those n. We see what is the slope, and we extend the slope to the whole bigger interval. And we do so for each group of n little intervals. And in this way, we are capturing exactly the slope every n little intervals. And okay, defining an interpolation in this way from a scalar function, we will move to vectorial function, and we say that our scalar function is converging to the vectorial one if the interpolations are converging in the topology we want. So I will begin with the coerciveness result. This is something very technical, and long to show, but fortunately the proof is not very different from the one already shown in the article by Braides and Cicalese. And so I won't be showing the proof of this. The main thing is that if we have a sequence such that our first order approximation energy are finite, then we know that we can extract a subsequence that is converging in L infinity to something in the domain I defined before. And also the derivative are converging L infinity, except for some points. I mean, in L infinity, every time we are far from some points, some critical points, which contains the jump points, but there can be also something more. Some more. Okay, so as I was saying, the limit energy will capture the transition energy, so we need a definition for the transition energy. Is again, as often happens in gamma convergence result, it's defined as a minimum of something. This expression will appear from the energy we have, and actually we can see this part is exactly our energy rescaled by something, rescaled by epsilon n. What I need to stress is the boundary condition. Okay, at least we are taking function on the integers, and the boundary condition is that after a while we are taking optimal oscillation. This you see is the function oscillating optimally. So before a given index, we are oscillating in the way we are coming from, and after a while we will oscillate in the way we are transitioning to. Okay, for some technical reason, we need another definition in which we allow some vertical translation, but from the C1 regularity, this is not a problem. Those and transition energy are actually the same for every vertical translation we want. Okay, so finally, we are arriving to our result. We have that the first order approximation energy is gamma converging to the sum over the jump sets of the transition energy of the two level we are jumping in between. Okay. So now we are gonna prove these results. At first, we noticed that okay, I didn't say what the additional term for the transition was. These are, so we have an additional term of M-range interaction, where the function RL is the tangent line to psi star star in the point L. Okay, so all we can recover that part simply using some property of a affine function. This is coming from the part of psi star star of L rescaled by epsilon n. So in this way, we can rewrite the energy as a sum of some energy density, this mathcal E, evaluated on the function rescaled by epsilon n. And this energy density is exactly the one appearing in the transition energy. So, okay, now let's move to the gamma limit inequality. So we take a sequence converging in the sense described before with respect to the L infinity topology to something in our domain. We can assume the energy to be bounded so that we can apply the equicursiveness result so that we can recover a very strong convergence also on the derivative, and we can find some singular points we will call them x1, x2 to xn. Also the limit function will have derivative piecewise constant. We call those constant C1, C2, some Cj, and those Cj will belong to some minimal sets of either L or some of the extremal points if we are in some bad interval. Then we will call Kj a particular approximate, the index that in our discrete setting is approximating in some way xj, and hj will be the index that in some proper way is approximating the midpoint between two singular points. So in this way, looking at the sum between hj and hj plus 1, we can localize the behavior of the energy around each singular point. So, okay, to proceed, we need to change our sequence of functions with something that belongs to something that is admissible for the minimal problem defining the transition energy. So we will make this change with U tilde. Okay, I put the analytical expression just because it's nice to have, but let's understand what is going on by a graph. So, okay, we focus around a singular point, which is basically a corner of our function. We translate and rescale it properly so that we can get rid of the epsilon n. And okay, now we need to extend the function to the whole integers. And how we extend it, we simply attach properly some function following the optimal oscillations. And okay, adding this point, this optimal oscillation is not a problem because one can see that for optimal oscillations, the energy density is 0. So we are not adding anything. Instead, what happens when we are, I mean, a little bit far from those dashed line is not a problem because the function is really preserving the energy density. The only problem is what is going on near the dashed lines, but this is only a problem for some finite amount of indices. So given the strong convergence we have far from the singular point, because near the dashed line we are far from a singular point, and also thanks to the fact that our energy density is continuous, we can recover the proper convergence. So this modification is not causing any problem. We can rewrite our energy, then we can estimate from below with the transition energy. Actually, the transition energy with some displacement, some vertical displacement, but this is not a problem, as we were saying before. And so we already have the gamma limit inequality, basically. Okay, for the upper bound, so the limit inequality, we basically do the same thing in reverse. So we take some function Vj, which are almost minimizer for the transition from from Cj minus 1 to Cj, so that the energy will be bounded from above with the transition energy plus something arbitrarily small. And then, okay, we need to link those function Vj together. We then translate and scale back and link all those Vj together. We are cutting the tails, but as we said before, this is not a problem because we are not really changing the energy. Okay, so those function Vj links well together. We are not cutting any energy by cutting the tails. the function we build in this way is converging as we want. I only make one further observation, is that for some technical reason, Y may need to apply some circular, some cyclic permutation of the indices of the cycles of slopes, but this is not a problem because our transition energy is stable under this kind of cyclic permutation, basically because making a cyclic permutation is just like translate our functions. And okay, I'm making this observation only because Matteo was very excited once we discovered this thing. So they're basically done. There's only the problem of forcing the boundary condition. If the alpha j are always L, this is not a problem. But when we are in some different cases, we have that we are not satisfying the boundary condition. So we need to introduce another perturbation. So our recovery sequence will be this U tilde n, defined as the previous sequence plus this delta nt perturbation. This is not causing any problem in the matter of convergence of the sequence because this delta n is going to 0. And actually is going to 0 as epsilon n. The problem is maybe for the energy. So okay, close to the critical point is not a problem because again this is involving only a finite number of indices. So by continuity, the error is disappearing. While far from the critical point, we can actually estimate the difference in energy between the U tilde and U, and this is estimated by this kind of quotient, which is recalling a difference quotient. And so by the C1 regularity, we can convert to, we know that this is converging to some derivative, and this derivative must be 0 because the unperturbed energy density is actually a minimum for that energy. And okay, this is when we found a recovery sequence, and so we have also the Lim-Sup inequality. And with this, we draw the better slides to talk. I'm done this. Okay.
So you are using the C1 regularity just for the continuity of the difference quotient.
We are using exactly for in the same way in 2 points here, and also to have the equivalence between the two transition energies.
Doesn't depend on this.
Also here. I'd say that this is the most critical. I mean, there are some criticality in the 2 points. If you remember, there were a slight mistake in the paper by Braides and Cicalese, and they were applying a different perturbation here, but this perturbation was not converging to 0. And the problem is that you have actually that you're scaling as epsilon n, you would need something better, but we don't have that. And okay, if we can somehow get rid of the C1 requirement, probably the gamma limit will use something of this form.
Sorry, Edoardo, but if I remember correctly, to prove that this psi with the xi is actually equal to the other phi, it is just Fermat theorem applied another time, right?
It's the same thing as
it's the same technique.
The last line, exactly.
Yeah, so we need to use only Fermat theorem, not C1, but something that such that Fermat holds
Yes, yes.
in some sense.
Yes, of course, of course.
Okay, so let's thank again the speaker.